Hi, okay, so the next talk will be given by Kumar from the Georgia Institute of Technology, and it'll be on predicting weekly stock
Thank you, Olivia. Thank you, everyone. And it's a great opportunity for me to talk about what I do partially what I do in my class at SIMI EXPO. I teach differential equations, and as like I've attended several talks today, and I saw that many people do single tank problem applications of differential equations relevant to single tank compartment analysis, multi-tank problem, logistic models, predator prey models, competing species. I saw several of people discussing that. And in addition to spring mass problems, I saw that as well. So in addition to those models, I discuss applications of second order differential equations to electric circuits. And towards the end of the curriculum, when I do the numerical methods to the first order initial value problem, which is Euler's method, I just follow this up with the discussion on predicting the stock movements, just to give them an additional application. And before the talk began, I was just casually talking, and I was mentioning how few of my students are computer science majors, and they have a minor in computer data analysis, and they find this topic finds traction with them. And this talk is very similar to what I presented at local high schools as a part of my outreach program as well. I try to develop an algorithmic approach to predicting the stock movements over a period of time. Needless to say, they're not precise, or they're not robust, but nevertheless, it gives a flavor to predicting the future stock movements. And the methodology that I outlined to them is first is data extraction. The second one is calculating the expected returns and expected volatility. Then introduction to the geometric Brownian motion. It's a huge topic, but introducing it in a very light flavor. And then simulation of the stock prices using the Python. And then at the same time, seeing some sensitivity analysis. How does the stock prices change when we increase the number of simulations? That's what we discuss in the class. It usually takes about, depending on the questions, can take anywhere between 30 minutes to 1 hour, not a very light, basically. What we do in the class is we pull up the stock data for any particular stock that is of interest using the stock history function. I'm sure this is, I mean, many of you might, a few of you or many of you might be familiar, but in my class, this is how I tell them. The first argument would represent the stock ticker symbol. The second one would represent the date from which we are extracting the data. The third one would represent the date until which we are extracting the data. The fourth argument would represent the time interval between two data points. If the fourth argument is 0, then we are extracting daily data. If the fourth argument is 1, we're extracting weekly data. If the fourth argument is 2, then we are extracting the monthly data. From once I get the monthly data, I just build upon it to go quarterly or annually, or just for the sake of simulation purposes. Now, the sixth argument represents the date, and the seventh argument represents the closing stock prices. Then after that, what we do is we pulled out. I just pull out. I try to. There are many popular stocks that among students, but I just want to focus on the Euler method, so I don't try to go for the popular one. So I just pulled out the stock price of stock M, let's say from monthly data from January 1st of 2008 to the January 1st of 2026. And from the monthly data, I generated the annual closing stock prices for the stock M. And that what is represented in the table. The second column represents the closing stock prices of January 1st. And the third column represents the percentage change in the value of the stock prices. Now, of course, we all know that the stock market is closed on January 1st, but on the internet, when I pull out the monthly data, that's what I got, and I'm just using for the simulation purposes, so just to illustrate the methodology. So I did not really go into the details of it. After pulling out this data, we calculate the annual parameters. The annual expected returns for the stock is 11%. The annual volatility or the risk or the standard deviation is 16%. As we can see that the volatility is greater than the expected returns, or expected volatility is greater than expected returns. And we'll come back to that observation very shortly. I mean, what we do is we may not, all the time, the students may not be really interested in predicting, in seeing the future stock prices or future stock movements over longer horizons. They might be interested in smaller horizons as well. So we discussed how to scale the parameters. So in a traditional year, there are about 252 trading days. That's what I looked up. When I looked up, that seems to be the standard 252 trading days, 52 weeks, and 12 months. So what we do is we scale the parameters from the annual data to the data over the sub periods. So if the daily expected means would be the annual data divided by 252. Similarly, so the weekly expected returns would be the annual data divided by the 52 weeks, and the monthly expected returns would be the annual expected returns divided by the 12 months. Now, the expected return scales linearly in time, so we are really nice with that. So then we discuss how variance scales linearly with time, but standard deviation doesn't. So standard deviation scales with the square root of time period. So the daily expected volatility would be the annual volatility divided by square root of 252, because there are 252 trading days in a year, and so on. And so we can calculate the expected weekly volatility and expected monthly volatility. So we calculate that. Then what we see is that when we evaluate the weekly parameters, weekly expected returns is 0.2%, but weekly expected volatility is 2.3%. So the weekly expected volatility is greater than the expected returns. So that's why in the shorter horizon, we see that the chart of the stock prices is more like a sawtooth or more bumpy when compared to the chart of the stock prices over the long run. Over the long run, they look more nice or less bumpy, but over the shorter, like if I'm calculating it over 5 trading days or 2 weeks or 3 weeks, it looks more bumpy. So we observe that. And then now we want to simulate the stock movement. We want to study the stock movements over a certain period of time, and we use a discrete geometric Brownian motion for that. And here delta S is a change in the stock value. Obviously, mu is the expected annual returns. Delta T is the time period. Now, if we are calculating, if we are measuring the stock movements over the days, we use delta T to be 1 over 252. If we are measuring the stock prices, stock movements over the weeks, then delta T would be 1 over 12. And if we are measuring it over monthly, it is going to be 1 over 12, and so on and so forth. And sigma would be the expected volatility, and epsilon would be the standard normal variable, random variable from the standard normal distribution, whose mean is 0 and standard deviation is 1. That actually models the unpredictable nature of daily news, geopolitical events, and daily trades, and so on and so forth. So at this point, we try to get the flavor of how this model works. Let's say in the discrete geometric Brownian motion, the first part is the first term on the right-hand side it represents the deterministic part, and the second term represents the stochastic part. Now, let's say if there is no stochastic part, that means there is no volatility, and everything is there is no unpredictability, and everything is very predictable, which is far, far, far away from reality, or that's not reality at all. So if we have the deterministic part only, then we the first term represents the growth that we expect to see, which is very similar to growth models in the population and so on and so forth. Now, the second part is the stochastic part that represents the volatility. It introduces the shocks to the system, and we see that we discuss how it kicks, how the volatility kicks the stock price off its chart because of geopolitical events or some news in the some unpredictable news. Now, what we do is we simulate in this slide, we simulate the stock prices. Stock prices. This provides a visual representation of stock prices using 10 Monte Carlo simulations over a period of 5 days. So, as you can see here, this will be day one, that will be day two, that will be day three, this will be day four, and the day five would be the terminal prices. So we can see that over the shorter horizon, the chart of stock prices is bumpy, and the stock prices cluster around the mean, which is 250.78. The average stock price on the day five is 250.78. $250.78. And for this simulation, the starting stock price is actually the stock price from January 1st of 2026 from our earlier table, which was approximately $253. So that's a starting stock price. And we ran the 10 Monte Carlo simulations, and the average stock price on the day five was 250.78. And we see over a shorter horizon that the stock price, the chart of the stock price is very bumpy. Now, what we did was we increased the simulations. So what we did was here is the visual representation of 100 Monte Carlo simulations of stock prices over a period of 5 days. So it's still bumpy, but we got more simulations. So we got more trajectories, and the average stock price seems to be the average stock price on day five after 100 simulations is 253.89. Once again, the starting point is the stock closing price from January 1st of 2026, and the stock prices cluster around this mean. Now, if we increase the number of simulations to 1,000, the average stock price on day five is 253.87. So you can see that with 10 simulations, the average stock price on day five is 250.78. With 100 simulations, it is 253.89, and with 1,000 simulations, it is 253.87. So we see that in the class that as the number of simulations increase, the average stock price seems to stabilize. So we ran about 10,000 Monte Carlo simulations, and the stock prices seems to cluster around 253.79. Again, it seems to be the average stock price on day five seems to be stabilizing. So this kind of graph helps us visualize that as we increase the number of simulations, the average stock price on day five seems to be stabilizing. Now, what we did in a class after that was we graphed histograms of stock prices on day five after 10 Monte Carlo simulations, because the number of simulations are obviously low. We can see that the histograms are very sparse. Now, if we increase the number of iterations, we see that there is a more recognizable picture evolving. And when we run 1,000 iterations, we see that even more recognizable graph evolving. And we can see that when we ran 1,000 iterations, the histogram of closing prices on day five will represent the log normal distribution. So now, what we saw was that we introduced the geometric Brownian motion, ran Monte Carlo simulations. We saw how the stock prices are stabilizing with when we increase more number of simulations, and we saw that what will be the distribution of stock prices as we increase the number of simulations. Now, that's a key result summary. So what we see here is we change the number of iterations we increase the number of iterations from 10 to 1,000. The average stock price really stabilizes around 253.79, and the standard deviation varies between 5.07 and 6.05. Using Python, we calculated what is the probability that the stock price is greater than the initial price, which is the closing price of January 1st, 2026. There is 53% chance that the stock price is greater than its initial price. This slide pretty much we executed all this in Google Colab. This is the Python code that we use, and this pulls this introduces the students to the geometric Brownian motion and Euler-Maruyama method, which is the stochastic counterpart of Euler's method. They study uh, um, um, Euler's method, Runge method, and they see a real life application in studying the stock movements using the Euler-Maruyama method. And this brings in a little bit of computing, so it brings in interest among the computer science students. Of course, there is Euler's method, so it brings in math and it also brings interest in from finance students. So we are trying. What I tried to do, but not so much at Georgia Tech, because at Georgia Tech the students are more motivated and they have already set their minds and goals on certain stuff. But elsewhere, I try to promote the growth mindset among the students with by relating what I do in the class with the real life. That's how and I use this. I use this kind of talks in my outreach activities to high school students as well. But coincidentally, now, if you really go back to see and what was the fifth day price of this particular stock actually in real life, it was $254.66. Of course, needless to say, we didn't get it right, but at least we got that it is greater than its initial stock price. That's what this is a project that not the project. This is some demonstration that I do in my class towards the end of the semester after we introduce the numerical methods. That's all I have. Probably my ending is very abrupt, but that's that's all I had. This is what I wanted to share.